Welcome to Spring LIB.
We are given these two half reactions that we have to algebraically manipulate in such a way to yield the given target reaction. We want to determine in part A what the value is of the equilibrium constant for the target reaction. So we first need to find the value of the standard cell potential of the overall given reaction so that we can use it in the Nernst equation to solve for the equilibrium constant K. We see that in order to get the form of the desired overall reaction, we have to flip the first given half reaction and therefore reverse its sign for its standard reduction potential. So we can write that out this way, where that standard reduction potential is now positive 0.444 for that first half reaction after we flipped it to undergo oxidation. We see that we have to multiply the second reaction by 2 now to cancel out those 2 electrons on each side. And so now we see that we have a total of 3 In plus aqueous going to In 3 plus aqueous plus 2 In solid, which was the desired reaction. And now when we add the potentials together, we can get the overall standard cell potential, which is equal to 0.318 volts. And now from the Nernst equation, we know that at equilibrium, the cell potential is equal to 0 volts. And the standard cell potential we just found was 0.318 volts. Then we do minus 0.0591 over N, and we see that we canceled out 2 moles of electrons times the log of K. And now we rearrange this to solve for K, and we should get a final answer of about 5.77 times 10 to the power of 10. And now in part B, we want to determine what the value is for the delta G of formation at standard conditions for In plus, given that same value for In 3 plus. And we know that we can calculate the overall delta G using the equation delta G at standard conditions is equal to negative N Fe at standard conditions. And N, again, is 2 moles of electrons. F is Faraday's constant, 96,485 coulombs per mole of electrons. And we just calculated the standard cell potential to be 0.318 joules per coulomb. And so when we plug that all in and solve for delta G, we see that it comes out to about negative 61.4 kilojoules. And now the generic way to find delta G from delta G of formation values is that overall delta G, which we just solved for, negative 64.1 kilojoules, is equal to the total change in Gibbs free energy of the products minus the total change in Gibbs free energy of the reactants. For the products, we have In solid, which is in its standard state and therefore has a delta G of formation value of 0. So for the products, we just have the delta G of formation value of 1 mole of In 3 plus. And so we are given the value for that delta G of formation value. So for the products, we just have 1 mole of In 3 plus times its given value of negative 97.9 kilojoules per mole for its delta G of formation. Then we subtract the delta G of formation for the reactants. We have 3 moles of In plus. So that's 3 moles times what we are solving for, the delta G of formation at standard conditions for In plus. And now we can rearrange this equation to solve for that delta G of formation value. And when we do, that'll come out to, in units of kilojoules per mole, about negative 12.2.